Hello everybody, this is Dr. Christopher White, and in this video we're going to be looking at the formation of precious metal mineral deposits. So we're going to begin by looking at gold and silver rich mineralization. So the first thing to note is that when we're talking about gold and silver rich mineralization, we are talking about mineral deposits which are mined primarily for gold and silver. Now, there are lots of different deposit types from which gold and silver are also produced, but they are being produced as a byproduct. They're not the main focus of mining. In the next few slides, we're going to look at some different deposit types, and they are going to be exploited primarily for gold and or silver. So the first type of mineralization that we're going to look at are veins associated with hot water. So these are gold and silver bearing veins that are created by the circulation of hydrothermal fluids. And these hydrothermal fluids are going to move through the rock and they're going to exploit whatever weaknesses they can find. So they're going to move along fractures, they're going to move along fault planes, and they're going to move along bedding planes. Essentially any kind of weakness where there's a gap, a hydrothermal fluid will move through it. Now, the origin of these hydrothermal fluids that host gold and silver are very wide ranging because there's lots of ways of producing hydrothermal fluids. So the hydrothermal fluid in question could be the result of heating of groundwater by magma. It could be a fluid that's formed directly from a crystallizing intrusion, so a magmatic fluid. It could be a fluid that's formed due to metamorphic reactions, so as minerals change from their original form to their new higher pressure temperature phase during metamorphism, you can sometimes release water as a byproduct, or the hydrothermal fluid could be the result of the liquefaction of a package of sedimentary rocks. So there are lots of ways that you can produce these hydrothermal fluids. The most important thing is that obviously they have to contain gold and silver. So where is that gold and silver coming from? Well, it has two possible sources. The first source is that as the hydrothermal fluid circulates through the volume of rock, it scavenges, so it picks up that gold and silver from the rock that it is passing through. And eventually, of course, there will be a change in the chemistry of the hydrothermal fluid, and that will cause the gold and silver to be precipitated. The other way in which the gold and silver can make it into the hydrothermal fluid is if that hydrothermal fluid is primary. So let's say it was created by a crystallizing intrusion. And so that means the gold and silver that's in that hydrothermal fluid actually came from the intrusion itself. So once we have our hydrothermal fluid and it contains our gold and silver, it's then going to obviously move through our package of rocks along any weaknesses it can find, and it's going to want to move upwards because of course it's hot, and so it's going to be quite buoyant. It's naturally going to want to rise. So if we look at the diagram here, we can see we have a weakness right here. This is our intrusion. So in this case, we're just going to say that we've got groundwater which is being heated by the intrusion, and as that groundwater circulates, it picks up gold and silver from the rock that it's passing through, and obviously because the water is being heated, it naturally wants to rise up along the weakness, and we end up with our mineralization along this fault plane. Now, in terms of what's driving the precipitation of the gold and silver mineralization, there's quite a few different options. So one of the ways is it could be due to some kind of fluid rock reaction. So as the hydrothermal fluid is moving, moving through the package of rocks, it comes across a layer of rock which it reacts with quite strongly. And these strong reactions will cause the chemistry of the hydrothermal fluid to change very rapidly. And this will cause the precipitation of minerals, including gold and silver minerals. Another possibility is simply cooling. As the hydrothermal fluid rises, it gets higher in the package of rocks, it moves towards the surface. Those rocks more towards the surface are naturally cooler, so the hydrothermal fluid starts to lose heat, and as it cools down, the capacity to transport dissolved metals actually decreases. So as a fluid gets warmer, you can actually dissolve more stuff in it. As a fluid gets cooler, you can dissolve less stuff in it. And so as your hydrothermal fluid cools down, its ability to carry the dissolved gold and silver decreases, and so it starts precipitating that gold and silver as minerals. Another possibility is that you have fluid mixing. So you simply have your gold and silver bearing hydrothermal fluid meets another fluid of some kind, and the mixing of those two causes the gold and silver to precipitate out. The final possibility is boiling, and this is typically associated with hydrothermal fluids which are produced from magmas directly, so they're a primary fluid. And so what you'll have is a fluid that comes off your cooling intrusion. It's very, very hot, but it can't boil because all the pressure from the rock around it stops that from happening. But then as your hydrothermal fluid begins to move towards the surface, the pressure drops, and eventually you get to the point where the pressure drops low enough that your very, very hot hydrothermal fluid will begin to boil. And when this happens, obviously you have a situation where a lot of the stuff that's being carried by your hydrothermal fluid is going to be dumped, precipitated out as your hydrothermal fluid begins to change from a liquid to a gas. So as you can see, the formation of gold and silver bearing mineralization by hydrothermal fluids is an extremely complex story because there's just so many variables involved. For instance, where does the fluid come from? Where is the gold coming from? And why does it precipitate? So the next group of gold and silver based mineralization we're going to look at are gold and silver veins associated with metamorphic rocks. So gold and silver bearing veins can be produced within metamorphic rocks by two processes. First process is that you have existing gold within your metamorphic rock, and during the metamorphic process, that gold becomes remobilized. So for instance, there's the possibility where you could actually reach a temperature where the gold minerals actually begin to start melting. And then, providing there is sufficient permeability in your rock, the gold melt that's produced can then start to migrate. It may migrate to a point where it begins to concentrate. So you end up with a body of rock that is enriched in gold. The other possibility is back to hydrothermal fluids again. So in this case, we have hydrothermal fluids which are being produced by metamorphism. So as one mineral changes into another mineral, you release water as a byproduct. This water then circulates through the metamorphic rock where it scavenges gold mineralization from that metamorphic rock. And it will then deposit that gold and silver mineralization when the metamorphic hydrothermal fluid comes into contact with a reactive layer of rock. So, this could be a layer of rock, for instance, that is quite rich in iron minerals. And so as the hydrothermal fluid comes in contact with that iron mineral rich layer, what can happen is you might get a chemical reaction between the hydrothermal fluid and the rock, which will cause the iron and sulfur in the hydrothermal fluid to react, and that will produce pyrite, which is iron sulfide. And of course, what you're doing there is you then suddenly start changing the composition of your hydrothermal fluid because you're taking sulfur out, and this change in the composition of the hydrothermal fluid is enough to start causing gold and silver minerals to precipitate out. Now, in terms of where these metamorphic hosted gold deposits are found, they are typically associated with high-grade metamorphic terrains because these are environments which have been very strongly deformed. So that means there's going to be lots of pathways for the hydrothermal fluids to circulate. It also means these are environments that have had quite a high heat flow. So there's going to be lots of essentially hot rocks around to actually heat up and produce the hydrothermal fluids. And these rocks have been exposed to higher metamorphic grades, which means they have gone through more reactions. So you've had more changes in the mineralogy. So that's more opportunities to release water, which essentially can then obviously go and form our hydrothermal fluid. So when we typically find these kind of metamorphic gold deposits, we tend to find them associated with areas which were once upon a time orogenic belts. So later on, when we look at the map of gold deposits in North America, you will notice that the vast majority of them are located within the Rockies. And one of those reasons is because orogenic belts like that, be they active now or be they ancient ones, like the Appalachians, for instance, those are the kinds of environments where, all that tectonism, all that magma, all that heating makes it an absolutely perfect environment for large fluid circulation to take place, leading to the formation of mineral deposits. The next type of gold mineralization we're going to look at is gold associated with gravels, and these are going to be our placer gold deposits. So in this situation, what we have is a rock which contains gold mineralization. Now, this starting rock does not have to be a super gold rich rock. It just has to have a few little gold minerals spread throughout the rock. So don't think that the source rock this is coming from is some kind of really high grade gold bearing rock that you could mine. It's not. It's just something like a granite. Okay. Now, this gold mineral bearing rock is going to be weathered because it's exposed to the atmosphere. And as the rock breaks down, it will release these gold minerals and they will become incorporated into the sediment being produced by the weathering of this rock, in this case, granite. Now, what's going to happen is the sediment is then going to be transported, or it's going to be moved around. So in the case of rivers, it's going to be transporting it along the river channel. In the case of a beach environment, the sediment is going to be moved around by waves. Now, the thing we have to remember about gold is that it is a very heavy element. So gold minerals are very dense. They have a lot of weight to them compared to other minerals of the same size. So what this is going to mean is that as the sediment that contains the gold is exposed to moving water, all the light clasts are going to be picked up by the water and transported away. Stuff that's going to be left behind is the stuff that the river cannot move. It doesn't have enough energy to move it. So that means you're going to be looking at stuff like gravels. So those are clasts which are too large for the river to move any further. But you're also going to be looking at minerals which are too dense for the river to move any further. And that's going to include gold mineral. And so what's going to happen is relatively early on, you're going to get a sediment forming in your river or in your beach environment, which is quite coarse. So you're going to have boulders, cobbles, and gravels. So, relatively coarse class sizes. And along with those coarser class sizes, you're going to have denser minerals like gold minerals all building up together. And so these coarser sediments are going to be what you're looking for. So what we have is a case of mechanical sorting. So in the end, what you're going to get is you are going to get either an unconsolidated sediment, which you can simply come along and dig up. So that's going to be your placer gold mineralization. So if you were mining that, you would simply find a river system that was draining an area which had gold-bearing rocks. And then you would know that, well, over time, as more of that rock got eroded, that gold would enter the river system. And so over time, your river sediments would become richer and richer in gold. And then you simply come along with your excavator, if the river has dried up, or your dredger, if the river is still active, and you just vacuum up the sediment or scoop up the sediment and then do a simple density separation to remove the gold from the other sediment. Now, in the event that the river sediment actually ends up becoming lithified and turned into a rock, what you're going to end up with is you're going to end up with a gold-bearing conglomerate. Okay, so the next type of mineralization that we're going to look at are gold-bearing conglomerates. So these are sometimes referred to as quartz pebble conglomerate gold deposits. That's quite a mouthful, but that's the technical term for them. And the particular type we're talking about are not the type that we were just talking about here. Okay, the vast majority of these gold-bearing conglomerates are actually metaconglomerates, so they've been metamorphosed. And they typically have a range of metamorphic grades. Some of them are low grade, some of them are high grade, but most of these gold-bearing metaconglomerates are relatively high-grade metamorphic rocks. They've been exposed to quite high temperatures and pressures. Now, the interesting thing is about gold-bearing conglomerates is that although the rate of deposition for gold-bearing conglomerates will have been relatively constant throughout Earth history, so you're going to be creating gold-bearing conglomerates today at the same rate you were creating them 50 million years ago, for instance. However, the majority of these quartz pebble conglomerate gold deposits are actually hosted in rocks between 2.9 and 1.8 billion years ago. So we're going to be looking at the Middle Archean to the early Proterozoic. So that's a bit strange because you would assume that these gold-bearing conglomerates would be spread throughout geologic time, but in reality, the majority of them are actually located in this window here. Now, this brings us to a question of why, and the simple answer is we don't know why. We know it's happened. We can see that there's this burst of gold-bearing conglomerates being formed during this time period, but the exact reason for why it's happening is still uncertain. So, we're just going to have to keep working on that one. Now, examples of gold-bearing conglomerates can be found across the entire world. So we can find them in the United States, Canada, Brazil, Finland, Australia, Ghana, the Ukraine, India. However, by far and away the best known example is the Witwatersrand Basin in South Africa, where you have a substantial gold-bearing conglomerate which is buried about 3 kilometers underground. And of course, they've sunk mine shafts to get down to it, and it's been producing gold for hundreds of years. Very, very productive area, and it's still producing gold now. So gold-bearing conglomerates are very interesting, purely because they have this very limited time range, and we don't know why. Also, in terms of what's forming them, it's a little bit uncertain. They are probably being formed in the same way as these placer gold deposits, and then the conglomerate that formed the conglomerate was then lithified, and then that conglomerate was then exposed to temperatures and pressures which cause it to become a metaconglomerate. So chances are these deposits are probably related to some kind of river or beach process, but it's just not particularly clear because these are such old rocks. A lot of them have been exposed to a lot of deformation, especially as most of them are moderate to high grade metamorphic rocks. And so this means that primary textures that might tell us how these deposits were forming have been destroyed due to the metamorphic process. So these gold-bearing conglomerates are a bit of an enigma. We know they're out there. We know the age of the rocks we should be looking at, but in terms of why they're forming, where the gold is coming from, why there's this relatively limited time range, we are very, very unsure. The next type of gold mineralization is low-grade gold deposits, and these are often referred to as Carlin-type gold deposits. So these are sedimentary hosted gold deposits, and the gold within them is invisible. You can't see it. You only really know it's there by actually assaying the piece of rock and chemically working out how much gold there is in the sample. So the gold itself is typically associated with a couple of minerals. Arsenic-bearing pyrite. So pyrite is iron sulfide, but this particular type has quite a lot of arsenic in there as well. And another mineral called arsenopyrite, which is iron arsenic sulfide. And so what we see is that this invisible gold, these tiny, tiny gold crystals, are located either within the pyrite or the arsenopyrite. Now, what is going on here? Well, once again, it's not hugely certain. We think we have an idea of what's going on, but it's not definitive. So what we believe is happening is that the gold is being transported by a silicon-rich hydrothermal fluid. And this hydrothermal fluid is probably magmatic in origin. So it's probably being formed by a cooling intrusion somewhere nearby, and that cooling intrusion pushes out a hydrothermal fluid, and within that hydrothermal fluid there is gold. And then this gold-bearing hydrothermal fluid is then moving along weaknesses, in this case faults, and eventually it reaches a layer of rock which contains a mixture of carbonate and muddy carbonate. And this gold-bearing hydrothermal fluid is coming into contact with these carbonate and muddy carbonate rocks. There's a chemical reaction taking place, and that causes the gold mineralization to be deposited, along with pyrite and arsenopyrite forming at the same time. And as the crystals of these two sulfide minerals grow, they enclose the gold mineralization within them. Now, the interaction between our hydrothermal fluid and our carbonate or our muddy carbonate essentially is due to the hydrothermal fluid reacting with carbonate minerals. So typically minerals like calcite are relatively reactive, so when they come into contact with a hydrothermal fluid, a chemical reaction may well take place. And this leads to the carbonate minerals actually being replaced by silicate minerals. And it's this change, this reaction, which is destroying the carbonate minerals and causing silicon to leave the hydrothermal fluid. That's what's causing the chemistry of the hydrothermal fluid to change. That change in the chemistry of the hydrothermal fluid is leading to the sulfides being precipitated. That is also going to change the chemistry of the hydrothermal fluid, and that's then going to lead to the gold being precipitated out as well. So our final type of gold mineralization is byproduct gold. And this is what I mentioned before, where you are producing gold not as the primary metal of interest, but it's just a credit, it's a bonus. So we have many economic base metal deposits, that's deposits that contain copper, nickel, zinc, lead, and tin, will also contain gold and silver mineralization in low concentrations. And so what happens is as part of the extraction of the metals of interest, you will then also extract a little bit of gold and silver mineralization there, because let's face it, you've already dug the rock up to extract the other metals, so that's where you're making most of your money. All you're going to do is you're just going to take the gold and silver as well, and you're going to earn some extra money on top of stuff you would get for your original metal of interest. Now, in terms of byproduct gold, it's commonly associated with copper deposits and magmatic nickel, copper, platinum group element deposits. So these are deposits that form due to intrusions, and these copper deposits, well, they can form through a range of different methods, but the majority of them are going to be of hydrothermal origin. In terms of silver, which is being produced as a byproduct, this is typically going to be produced as a byproduct from gold deposits. So the gold deposits we've just been speaking about will typically have a little bit of silver mineralization as well, and that silver mineralization will be taken out as a byproduct. You will also find silver mineralization associated with lead mineralization, with zinc mineralization, lead mineralization, and tin mineralization will have silver minerals present in low abundances. And so you can also use the silver and extract the silver from those kinds of ores as well. Now, the gold and silver concentrations for these deposits can typically be quite low. And because they are not the metal of economic importance, they are not the main focus. So, you're going after, let's say, the copper, but you're going to take the gold as a nice added bonus. And because they are an added bonus that earns you additional money, they are typically referred to as credits. So a gold deposit that produces gold as a byproduct has a gold credit associated with it. So you're there for the copper, but you're getting a gold credit as well on top of the copper metal that you're extracting. Now, if we look at the distribution of large gold deposits in the United States, you will instantly spot that the vast majority of them are associated with this area of elevated terrain over here. And this isn't a coincidence. This is because a lot of gold mineralization is associated with orogenies, mountain building events. Now, why is that? Well, when you are forming mountains, there's a lot of stuff going on. There's obviously a lot of compression, which is going to lead to a lot of faulting, and folding and fractures opening up. And this is going to be perfect for hydrothermal fluids in particular to circulate around. You are also going to have a lot of metamorphism related to regional style metamorphism, so moderate to high pressures and temperatures. This is going to lead to metamorphic reactions taking place, releasing water, and that water can then move around through our package of rocks, scavenging gold and silver as it goes, and then depositing that gold and silver somewhere else. We're also going to have a lot of intrusions in the area as well. So areas like ocean continent convergent boundaries like the Andes and even the northwestern area of the Rockies. So we're looking at Washington State and Oregon. They have active volcanoes at the moment, so we know there are intrusions in this area. And those intrusions, once again, they are going to maybe produce magmatic fluids that contain gold, or the presence of the intrusions is going to allow fluid circulation to take place, leading to gold mineralization being formed. So it's no great surprise that you have all of this gold mineralization associated with the area of the United States which has undergone the most recent orogenic event. Now, you will also find this occurring in other places where you have very ancient orogenic events that happened a very long time in the past. So you will have gold deposits in Canada which are related to things called greenstone belts. And these are forming all the way back in the Archean, but nevertheless, they are the result of a collision between bits of crust. So they are orogenic in their origin, and the same process was occurring all the way back in the Archean, and it led to the formation of gold deposits then as well. And those gold deposits are currently being mined in Canada, for instance. So typically, if you are looking for gold deposits, your first port of call is very often going to be, right, is this an area that has undergone some kind of orogenic event either recently or during the past? The final type of mineralization we're going to look at is platinum mineralization. So there are only a few locations in the world which are primarily mined for platinum. The vast majority of platinum group metals are going to be produced as byproduct. So you're going to be mining something else, and the platinum is just going to be a credit on top of that. Now, unlike gold and silver mineralization, which is primarily associated with hydrothermal fluids, platinum mineralization is typically found in mafic to ultramafic intrusive igneous rocks. So why is that? Well, in order to make these mafic and ultramafic magmas, you need to melt mantle rocks. You need to melt mantle peridotites. In the case of mafic magmas, you are partially melting your mantle peridotite. In the case of ultramafic magmas, you are fully melting your mantle peridotite. And the thing about mantle rocks is they are way more rich in platinum group elements when compared to the crust. And so the magma that you are producing by melting these mantle rocks is going to contain considerably more platinum and palladium, for instance, versus rocks from the crust. And so obviously once you produce your magma, it's then going to want to rise, and it's going to rise into the crust. Now, in the case of most ultramafic and mafic magmas, they never make it to the surface. They get stuck in the crust, and they form a magma chamber which slowly cools over time. And what we're going to see is that the platinum minerals tend to crystallize out relatively early from our cooling magma. And so in the very, very first stages of our mafic and ultramafic magma cooling down, these precious metal minerals, these platinum minerals, will begin to form. And because they're so heavy, they will begin to sink down to the bottom of our intrusion. They'll form a layer at the bottom. And this layer will often be associated with other relatively early forming minerals. And so along with the platinum minerals, you're also going to get other minerals like olivine, pyroxene, and chromite. These are other minerals that form very early as your magma is just starting to cool down. Now, by far and away the best location for platinum mining, where platinum is the primary metal being mined, is the Bushveld complex in South Africa. And it is the world's largest source of platinum. So it accounts for 75% of global platinum resources and approximately 50% of global palladium resources. So this is an extremely rich area for finding platinum mineralization. In terms of the Bushveld complex itself, it's the world's largest intrusion and its composition is ultramafic to mafic. So we know that this magma formed from the melting of mantle rocks, and it produced a very, very large volume of magma that moved into the crust where it got stuck, and it began to crystallize out minerals. And one of those early minerals that began to crystallize out was were platinum minerals, and they became incorporated into other early forming minerals. And so if we actually look at the picture down here in the left, you can actually see one of these areas where this platinum mineralization is hosted. So you can see these larger brown crystals. These are going to be pyroxene. Mixed in with them, there's going to be some black stuff. That's going to be chromite. And then within this area here, you're going to have these tiny, tiny, tiny crystals of platinum minerals, which are so small you can't see them in the picture. And this is the kind of rock you're going to be looking for, and it's going to form a layer that extends across the entire bottom of our intrusion. Now, in terms of mineral deposits where platinum is the primary mineral of interest, you are going to find that those deposits are very old. So in the case of the Bushveld complex, it's over 2 billion years old. So the question is, why is that? Well, the thing about the formation of ultramafic magmas in particular is that they were far more easily formed in the Earth's early history, when the Earth's interior was considerably hotter. Because of that extra heat, it meant that melting mantle rocks was easier, and so you had the capacity to form very large volumes of ultramafic magma, which could then move into the crust. In the modern situation, the Earth's mantle and the Earth's interior has cooled down. That means you are producing less ultramafic magma, and so that means you are not going to be forming these really, really huge ultramafic intrusions which you got in the Earth's early history. And so that's why you tend to find that these platinum deposits are quite old, because you need those large volumes of ultramafic magma in order to actually form them. Once you start producing less and less of it, you're going to get smaller and smaller deposits, which most likely will be uneconomic. All right, thank you for watching the video.